Hello and welcome to this tech talk about introducing quantum computing on AWS. My name is Eric Kessler. I'm a product manager for AWS Bracket, and I'm super excited to give you a deep dive into the service today. But before we get started, I wanted to give you a quick introduction about quantum computing and also explain to you how we at AWS see that technology. So to start with an executive summary slide here, what is quantum computing? Quantum computing or quantum computers are devices that use the physical laws of the microscopic world, namely quantum mechanics, to perform computations in a new and improved way. That means quantum computers behave according to these laws in a different way than classical computers do. And it turns out that these laws allow quantum computer for certain types of problem to be much more powerful. And I say here in a little bit of a sloppy way that you don't have to expect a 10x performance improvement, but the 10 to the power of x. And what I really mean with that is that full-scale quantum computers have the potential to solve computational problems that for all intents and purposes are intractable for classical computers. But of course, that comes with a huge caveat, right? Because we don't have for these quantum computing devices at that scale today, and it's an extremely hard scientific and engineering challenge to build these devices at scale. So where are we today? Today, we're just entering what's called the noisy intermediate scale quantum regime, which is far from the end goal where we want to be, but it's a promising start for early explorations. So when I said before that there are important applications and use cases, computations where quantum computers can outperform classical computers, it's not some toy problems. These are real world and high value applications across many different verticals, from computational chemistry, where, for example, the process of nitrogen fixation underlies the most prominent way how we produce fertilizer today. And if we had a quantum computer with just 200 qubits, we could simulate that process for the first time and perhaps develop a much more efficient approach to this. Similarly, for material science, with just 70 qubits, we could simulate high temperature superconductivity and find materials that conduct current without any resistance. Also in the field of optimization, for search, for ranking, for machine learning, with about 100 qubits, there are problems that can have a significant speed up compared to classical approaches. But of course, again, this comes with a big caveat. These numbers that I just told you about, these assume perfect qubits with no noise. And we know in the devices that we have access to today, there is a very high level of noise, and we have to counter and fight that noise through something that's called quantum error correction. And that comes at a cost. So you have to encode your information in a redundant form, meaning that instead of putting a piece of information in a single qubit, you have to encode that piece of information in many qubits. And that overhead can be very significant at the noise levels we are today. So if we look at the actual qubit numbers after correcting for noise, we look at 200,000 qubits for the computational chemistry example. We look at 100,000 qubits for the superconductivity example. And for optimization, we would need 500,000 qubits. Of course, this is all a little bit hand-wavy. There's a lot of detail to it, but in the order of magnitude, that is true. And if you think about the size of systems that we have access today, that is a very big gap. Today, we're talking about devices that have maybe a double-digit number of qubits. So there is a big chasm to that area when we have computational devices where we know we can solve high-value use cases and where we are today. So what is in between? Let's have a look at this diagram here, where at the bottom of the x-axis, we have the number of qubits, and on the y-axis, we have the error rate, or the number, or the noise in the system. So the lower the error rate, the better the system is. So we're just saying with hundreds of thousands of qubits and pretty low noise rate, we have high value use cases where we can prove that quantum computers can outperform classical computers to a degree that we can do for the first time things that we have never been able to do before. And then on the other end of the spectrum, everything below, say, 50 qubits or systems that have very high noise, we can prove that these systems cannot outperform classical computers for any use case. Now, where we are today is an interesting point, because we're sitting right before this big chasm, this big area number 2, where we know we can do computations that classical computers can't do, but we don't have a proof that these computations will outperform and will be useful to solve a real-world problem. So really the only way to find out what we can do there is, well, of course, we want to get to the end goal of having these fault-tolerant, as you say, quantum computers. And in the meantime, the only way to find out if there's anything in between is to build these machines and try it out. And against that background, we have announced in December of last year our approach to quantum computing at AWS. And it entails 3 different pillars at a high level. First, we have announced the AWS Center for Quantum Computing. That is a research center located on the campus of Caltech, where we're trying to push the boundaries. We know this is an area, and I mentioned before, there are large engineering and scientific challenges ahead of us, and we know that we need to still push the boundaries and contribute to the scientific advancement. And the Center for Quantum Computing is trying to contribute through original research in quantum algorithms and quantum hardware. We have announced the Amazon Quantum Solutions Lab, where customers can collaborate with AWS experts in quantum computing, but also HPC and machine learning to understand and start research in quantum computing for their specific use cases. And then lastly, and the topic that we're talking about today, is Amazon Bracket, a fully managed AWS service that makes it easy to explore and experiment with quantum computing. So let's dive a little bit deeper into that. So as I mentioned, Amazon Bracket is a fully managed service on AWS that every customer can access today. And the goal is to provide a single access point for different types of quantum computing hardware and allow customers to experiment and explore quantum computing. We provide fully managed development environments where you can build and design your quantum algorithms. You can test them against local and fully managed high-performance simulators in the cloud. And you can also run these circuits and these problems on a range of different types of quantum hardware on demand and secure. So to give you a little bit of an idea how Amazon Bracket works, let me walk you through a very typical process flow here. As a user, you can choose to use our Amazon Bracket notebooks, which are fully managed Jupyter environments that you can start with a single click from your AWS console. I'm going to show you in a little bit how to do that. These notebooks come pre-installed with the Amazon Bracket SDK, which is a programming framework that allows you to program quantum computing circuits and annealing problems and submit them to the Amazon Bracket API. So you would write your problem, you would write your algorithm in a notebook, or if you choose on your local IDE, and submit that to the Amazon Bracket API, and you can run these circuits or annealing problems either on managed simulators or on different types of quantum computing hardware. And you can choose the different devices by switching a single line of code in your Bracket SDK. The result of these circuits come back and they're being persisted in an S3 bucket in your own account. So S3 is AWS's object storage service. So the data comes back into your account and is under your full control and then flows directly into your notebook if you wish so. And needless to say, Amazon Bracket is fully integrated with other AWS services, from identity access management, for logging and monitoring, and also event-based processing. So we have services like IAM, Amazon CloudWatch, CloudTrail, and Amazon Event Bridge to help you integrate your work into AWS. So today, Amazon Bracket provides you secure and on-demand access to 3 different types of quantum computers. That is a D-Wave quantum annealer, an ion-based quantum computer from IonQ, and a superconducting qubit-based quantum computer from Rigetti. One thing I wanted to point out about the different QPUs you can access through Amazon Bracket is that they're tied to a particular region in AWS. So for example, the IonQ QPU is located closest to the region in US East 1 and therefore accessible through that region. Rigetti is integrated into US West 1. D-Wave is integrated into US West 2. However, the Amazon Bracket SDK makes it really easy for customers to access different devices by just changing a single line of code. Depending on the backend and device that you choose, the Amazon Bracket SDK will automatically route your request to the correct endpoint in the respective region of your quantum hardware provider. With that, let us jump over to the demo and dive into how we can use Amazon Bracket to run quantum circuits and quantum annealing problems on the different quantum computers on Amazon Bracket. So here you see the landing page from Amazon Bracket. We have different resources that you can access, information on our pricing. We link to the documentation, our hardware providers, and an FAQ to get you started. When you land here, you probably first want to look at the devices that we support. You can go to our devices page. You see basic information on the different providers. You see that the D-Wave machine is currently available. IonQ is in online status, but we don't have a reservation window now. You see the number of qubits and the region where these devices are located. To get started, you can open the notebooks page. And as I mentioned before, you can choose to create a notebook instance from here. You can also alternatively choose to download the Amazon Bracket SDK. It is open sourced. You can find it on GitHub, and you can use any IDE that you like. If you want to create a notebook, you can just click here, choose a name, and you have the option to choose from different EC2 instance types. For now, we're going to choose an T3 medium instance, which is the most cost-effective one. But if you want to have more computational power or more memory, you have the full choice of AWS EC2 and Amazon EC2 instance types that you can choose from. You have additional settings around the volume size that you want to attach to that instance type, and you can here also choose different permission, encryption, and networking options. You're required to choose an IAM role. And what does that mean? The IAM role essentially allows the notebook to perform actions on AWS on your behalf. So for example, it will allow the notebook to access the Amazon Bracket API. So you don't need to do anything but choose create a new role, and Amazon Bracket will create the default role for you. If you're a more advanced user and you want to have more fine-grained control about the access permissions for your notebook instance, you can always choose to provide a custom role for your notebook. But for now, we're just going to choose to create a new role that will automatically be attached. I opt in to root access, meaning I can access my notebook as a root user. And I do not choose an encryption key, but that's also an option that you have to manually choose the key. If you don't choose anything here, Amazon Bracket will still encrypt your data, but through an AWS managed key. So we can create this notebook instance. And while it is pending and spinning up, I'm going to go ahead and open a notebook instance that I have prepared. So you see, we click on the button and we land directly in the Jupyter Files system. Here we have a folder with Amazon Bracket examples that have a couple of tutorials and quick starts to help you get started on Amazon Bracket. For now, we're going to choose a quantum annealing problem. Quantum annealing, again, is working through the D-Wave device. And we have a couple of examples here. Let me pick one to show you how you can send an annealing problem to the D-Wave machine through Amazon Bracket. First of all, we're going to import a little bit of boilerplate here. I'm not going to go into much detail. Now, I mentioned before that all the results are being persisted on Amazon S3, which is our object storage on AWS. And it is going to live, the data that comes back lives in your account. So here in this step, you need to choose the S3 bucket where the results are being stored. When you sign up to Amazon Bracket, during the onboarding, Bracket automatically creates a bucket for you that starts with Amazon Bracket and a random string at the end. But by default, Amazon Bracket has write permissions to all buckets that start with this string. So I have created a bucket that ends in my account ID, and I automatically populate that here through that piece of code. So you can choose any bucket that you like, as long as it starts with Amazon Bracket. So I'm going to set up my S3 folder here, and I have to provide that whenever I run a problem, and then the output will be stored in that bucket. So what we're doing here now, we're instantiating what we call the Bracket sampler. So this is now a D-Wave device that we instantiate in the SDK. We have an embedder that additionally helps us embed the particular problem we're looking at into the device and into the graph of the device. And now we want to solve a very prototypical problem on a D-Wave device, a problem that's called minimum vertex cover problem. And so what are we trying to do? So we're starting from a graph with nodes and edges. The blue balls are the nodes, the black lines are the edges. And the goal of the minimum vertex cover problem is to color in these nodes, the balls, in a different color in such a way that, say, the different color is red, and in such a way that every edge touches at least one red ball. And we want to do it in such a way that we use as little as possible red balls that we color in. Now, so we start, it will become more clear once we do an actual example. So we start with this particular graph, and now we can run this problem on an actual D-Wave device. So with this line, we're going to send the problem to D-Wave, and we're going to get the result back from this computation. And you see the solution that D-Wave found was you need to color in the central node, which is obviously the solution here. Yeah, this is only one color change that we need, and every edge is connected to this red node. Now, of course, we can do this in more complicated graphs. So this is a more complicated graph, and we can send that problem to the D-Wave device. And in a similar fashion, we will get the results back with a particular solution to this problem. So next, let us see how we can run a circuit-based example on Amazon Bracket. For that, I'm going to navigate to the simple circuit algorithms example, and we're going to open this first example notebook. Again, we import some libraries here at the beginning. Again, we need to choose our S3 bucket. So again, I choose the bucket that I have previously created with my account number as an identifier. I set that up. And then we want to create what is called a GHZ state. So the GHZ state is essentially a quantum state where all the qubits are simultaneously in state where they all point to 0, and then together with the state where they're all in state 1. So it's a maximally entangled state, a kind of prototypical quantum information processing state. It's a very simple circuit that looks like this. So we do a Hadamard gate on the first qubit and then a series of CNOT gates. So this is a representation of quantum computing operations in this circuit diagram. And we can execute that on a real quantum computer. But before we get there, let's set up the circuit and let us see how we can first understand the result on a simulator. So this is a small function that creates a GHZ circuit, a circuit that prepares GHZ state. So we can see in a couple of lines, I can create a function that spits out GHZ circuits for n number of qubits. So let's create a circuit that creates a 10 qubit GHZ state. And we can look at that circuit and you'll see this is exactly what we had up here. So now the Amazon Bracket SDK, which we're in at the moment, comes with a local simulator. So we can set up the local simulator as our device. So everything we're gonna operate on now is gonna happen right in the SDK. So on the instance that you've chosen for your notebook. And we can simply take that device and do device.run, give it the circuit that we created, specify the number of shots, and then look at the results. And we can print the output. So it found 513 times all the states in 0 and 487 all the qubits in state 1. So this is a signature that we would expect. We can also visualize that here. And that's exactly the signature we would expect from a GHZ state. Now, the Amazon Bracket SDK also allows you to create different types of results, or different result types, other than just the regular sampling from the output. So for example, I can just take the circuit and make dot state vector to get the state vector as a result. I can get the amplitude of a specific state, or I can get the expectation value of a specific observable, or I can get the marginal probability here in this example of qubit number 2, for example. So I can do the same thing again. And now note that I've chosen shots to be 0. I'll explain to you what that means in a little bit. But you see, we get all the result types that I've requested. So what does it mean, shots equal 0? When I was running before, I had a finite number of shots. That means the simulator was emulating a quantum device. It was sampling from the output distribution. And that's the behavior that quantum computers follow, because they're intrinsically probabilistic, and we have to repeat the same measurement over and over again to build up the statistics. However, since we're simulating, we have access to the full state vector. In principle, we don't need to sample from the output distribution. We can just return it or calculate exact quantities from that output distribution. And so by just choosing shots equal 0, we're switching between these two modes. So when shots are equal 0, we get the exact results without shot noise, as one says. If we're choosing a finite number of shots, we're emulating a quantum computer, so to say. Okay, so this is the local simulator. Now, Amazon Bracket also provides access to a fully managed high-performance simulator in the cloud, and we can set that up using this line here. So now we're instantiating our device as SV1, State Vector Simulator 1. And because this simulator is running in the AWS cloud, entirely managed by Amazon Bracket, it is elastic and you can run multiple circuits in parallel. And this is what we're going to do now. So we're now going to simulate 10 circuits of GHZ state from 25 to 34 qubits, and we're all going to submit them in parallel to Amazon Bracket. So you see where before we were calling the results right away, we're now separating that command into a task creation. So we're creating a number of tasks here, but we're not asking for the result just yet. And that allows us to asynchronously submit a number of tasks and then retrieve the results later on. So I can run this cell. So first of all, we're cycling through creating these tasks, shipping them off to Amazon Bracket. And under the hood, Amazon Bracket is processing all these tasks in parallel. And once we're done here, you'll see the individual tasks coming back. This is the second code block. Because they were running all at the same time, we're gonna, at the moment, ask only for the results up to 30 qubits, because the larger circuits take a little bit longer to run, and we can come back to those results in a little bit. But you see that allows you to simulate much more effectively. If you need to process multiple circuits in parallel, this feature allows you to save a lot of time by not sequentially processing these on your local machine, but you can really scale out into the cloud with multiple parallel executions. So now we also want to run on an actual quantum computer, and all we need to do, where before we were setting up our simulator device with this line, now only we need to do is to replace this with the what's called an ARN, essentially the identifier of the Rigetti device in this case. Now all devices on Amazon Bracket come with a number of properties. You can access the device properties just like this. And we have a lot of information about the respective backend, the supported operations. We have the supported result types, different, the connectivity graph, how are the qubits talking to each other. We have the calibration data. So you see the noise for individual operations between different qubits. So there's a lot of information to access for you here. So now we're going to set up a small GAZ circuit, and we're going to run this on a Rigetti device. So this is very simple. Again, we just call the device, which I named the Rigetti in this case, and call a .run together with the circuit. We specify our S3 folder and the number of shots. Again, we have separated the creation of the task from the retrieval of the results, so you can check the state of the Rigetti task. It is already completed, and we can access the results here. So you see there's of course some measurement imperfection here because this is a real device with real noise, but still you see the main signature of the GAZ state where most of the results turn out to be in 111 or 000. We can also access the compiled program. So what happened here, to make a step back, when we submitted the Rigetti circuit, under the hood, there were a number of compilation steps to compile the circuit onto the actual Rigetti device. And we can access the final compiled circuit. So you see here, instead of circuit 1, 2, 3, it was mapped onto the actual qubits on the Rigetti device number 32, 33, and 34, because it takes into account the actual noise levels on the different qubits. And so this is the actual circuit that was executed on the device. So now to come back to our simulator results, we can retrieve those now, as I mentioned before. So by now, all the larger circuits also have completed, and we can return. So the 34 qubit task seems still to be running, so let me interrupt this for now. But we can access these in an asynchronous fashion. Now, we can go back to our console here, look at the different devices. And as I mentioned before, an IonQ quantum computer is currently not available, but you see here, you have the device ARN right in the console. I can copy this out, go back to my script. So this is exactly what I need to put in here. We can still instantiate this and try to run a circuit on IonQ. Again, it's the same syntax. We run this on this device, and you see the status changes from create to queued. Because the device is currently not online, it will stay in the queued status. So instead of waiting for the device to come online, we're going to cancel this here. And we can navigate back to our console and look at this task. So you see we have the task that I just canceled is here in our console. You see other tasks that we have kicked off previously. And I can go into the task detail. I see additional information about that. Once we have this task completed, you can access the results on S3. I can navigate back to a different task. Let's take this one, for example, and it takes me to my S3 bucket on AWS, and you can see the results JSON here. You can download this and access this through that way as well. So this concludes my demo of Amazon Bracket. Thank you very much for your attention. I hope you were able to learn a little bit about how to access quantum computers through Amazon Bracket, and I'm really looking forward to your questions during the Q&A.